Today we're getting into exponential growth and decay, and today we're going to have to set up our own equations. The other day when we did exponential functions, they just gave us the equation because they were sweet like that. But, you know, the form is y equals a times b to the x. It's a little complicated. I prefer to think of it like this way. Y is the final amount. The a is the starting amount. That number does not have an exponent on it, but it's always times something with an exponent. So the thing with the exponent, I like you to think of it as like 100% plus or minus the change. So if it's growth, we'll add it to 100%. If it's decay or depreciation, we're going to subtract it from 100%. And we always want that in decimal form, which we've practiced and we'll practice again. And then the exponent is always going to be the number of periods. All right, let's kind of set up our first one, and you'll see what I'm talking about here. The population of the Floridian beetles triples every 8 months. Now, obviously, I made that up. I don't know that. If a warehouse started with 14 beetles, find the new amount of beetles after 8 months, 24 months, 6 years. Whoa! So let's get a general equation here. Let's say y equals the starting amount of beetles. We started with 14. So that's going to be the number out in front. Times. Now, we're thinking 100%. It's saying it's tripling. So that would be 300%. But we always want it, the decimal version of that. So the decimal version of 300%, you just move the decimal 2 places to the left. It becomes 3.03. And then the exponent is how many times this is happening, the number of periods. So here's our general equation. 14 times 3, 14 is the starting amount, the 3 is from it tripling, and then the x will be the number of 8-month periods. All right, so now let's figure out how many how many beetles there will be in 8 months. So we'll have y equals 14 times 3 to the x. Now we're not substituting in 8 for x. X is the number of 8-month periods because it triples every 8 months. So how many 8-month periods are there in 8 months? Just one. Boop. So it's going to be 14 times 3 to the first. Now 3 to the first is just 3. So it's just 14 times 3, which would be 42 beetles. Great. 8 months, it tripled from 14 to 42. Now let's check 24 months. Y equals 14 times 3 to the, we have to think, how many 8-month periods are there in 24 months? Easiest thing you could do is just divide them. 24 divided by 8. So that means there are 3 8-month chunks in 24 months. So it's going to triple 3 times. So we do our exponents first. 3 to the third, 3 times 3 times 3 is 27. And I don't know what 14 times 27 is. 378 beetles. The beetles are getting out of control here. And then 6 years. Now, here's a toughie because it tells us that it triples every 8 months. And now they're like, whoa, what about 6 years? Ugh! We're going to have to figure out how many months that is. So, how many months are in each year? There's 12 months. So we could do 6 times 12, and that would give us 72 months. And you're like, oh, well, how many 8-month periods are in 72 months? Luckily, we could just divide it by 8 months. 72 divided by 8 is 9. So it's going to triple 9 times. So let's see, 6 years. We're going to say y equals 14 times 3 to the 9th because there are 9 tripling periods. 3 to the 9th. Holy cow, that's a big number. 19,683. We still have to multiply by 14. 275,562 beetles. You're probably just, the carpeting is beetles in this warehouse, or probably concrete. Just like crunch, crunch. Great. We started off with one of the tougher examples. The population of Geneseo, Illinois was 6,000 in 1991. The population continually increased 2% per year since then. Find the estimated population today. What will the expected population be in 10 years? All right. A few things. Our starting amount is 6,000 times the number with the exponent. We want to think of it starting at 100%. Now it's increasing 2% per year. So we're going to add that to the 100%, which gives us 102%. But we take the decimal form of that, which would be 1.02. This is going to be the number with the exponent, 1.02. So here's our general equation. We're going to figure out the estimated population today based on this equation that, again, was made up. Now, how much time has passed from 1991, when this fake data was created, to today? Now, I'm recording this video in 2024. You might be watching this 50 years in the future. Enjoy. I'm probably a hologram at that point. So to see how many years have passed, we could just subtract 2024 minus 1991. 4 minus 1 is 3. Ooh, gonna have to do some borrowing here. 12 minus 9 is 3. 19 minus 19. So 33 years have passed. So that's what we're going to use as our exponent. Now, this is going to give us a real sloppy decimal, and that's okay. But we're going to do the exponent first, 1.02 to the 33rd power. I have 1.922231404. Great. I don't need to write that. I'm just going to go ahead and hit times 6,000. And it has 11,533.3. Now we're going to round to the nearest human. We don't have any third humans here, so we're going to round that to 11,533 people. Delightful. Now, again, I don't think that's true. I don't think there's 11,000 people in this town currently. But hey, we did a math problem. You invest $300 in an account that pays 4% compound interest every year. Find the balance in the account after 4 years, 6.5 years, 25 years. Oh, I forgot to do part B of the last one. Thanks for reminding me. What will be the population in 10 years? So I think our initial equation was 6,000 times 1.02 to the x power. So we had said that today, today 33 years have passed. We're saying, how about 10 more years from now? So in 10 years, that means 43 years will have passed. So we're going to do 1.02 to the 43rd power, 2.34 blah, 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 times 6,000. Wow! So in 10 years, according to this fake made-up formula, there's going to be 14,059 people in Geneseo, apparently. All right. Sorry I forgot that one. All right, here we go. Back to this one. So starting with the general equation, the starting amount that we're putting in this account is the $300. The number with the exponent is starting at 100%. Now we're getting interest. We're getting more money. So we're going to add that to the original 100%. If I'm getting 4% interest, 100 plus 4 is 104. Now 104% in decimal form is 1.04 to the x power. So the x is going to be the number of years. Find the balance in the account after 4 years. So let's try putting in 4. 300 times 1.04 to the 4th power. 1.04 to the 4th, whoops, it's 1.1698, more stuff, times the initial $300 we put in, and we're talking dollars here, so we'll round to the nearest hundredth. I have $350 and 96 cents if you round it. So after 4 years, we have 350 bones. Now let's check 6.5 years. Y equals 300 times 1.04 to the 6.5 power. 1.04 to the 6.5 power is 1.29 other stuff times 300 is $387 and 11 cents. That's the 6.5 years. And now we got to check 25 years. Oh man, we're going to be loaded. 300 times 1.04 to the 25th power. 1.04 to the 25th. 2.66 and some other stuff. Times 300 is 700. Oh yeah. 799.75. Look at us. In 25 years, we're going to be rich. Woo! All right. Okay. All righty then. The half-life of fossilized lemon is 100 years. So every 100 years, this fossilized lemon, the amount of it gets cut in half. If the original sample of lemon was 300 grams, find the amount of fossilized lemon after 200 years, 350 years, 1,000 years. Let's get our original equation. All right, so we're starting with 300 grams. Now, this number starts as 100%. We're saying half of that. Half of 100% is 50%. In decimal form, that's 0.50 or 0.5. So here's going to be our equation. Cool. And x is going to be the number of 100-year periods, because this fossilized lemon gets cut in half every 100 years. So when they say, well, how much is left after 200 years? How many 100-year periods are in 200 years? 2. So 0.5 squared, oops, 0.5 squared is 0.25 times 300 is 75 grams. In 200 years. All right, let's see. How many 100-year chunks are there in 350? Well, in 300, there's 3. In 400, there's 4. So in 350, that's going to be 3.5. Y equals 300 times 0.5 to the 3.5. 0.5 to the 3.5 power is 0.088 times 300. We're going to have 26.5 grams. In 350 years. Not a lot of fossilized lemon here. And then the last one after 1,000 years. How many 100-year chunks are in 1,000? It's times 10, right? So there's 10 chunks where it's getting cut in half. Y equals 300 times 0.5 to the 10th power. 0.5 to the 10th, boom, times 300. Not even a full gram. 0.3 grams in 1,000 years. Wow, that fossilized lemon really just drops off, doesn't it? All right, and then we're going to go with probably the most applicable thing here, depreciation of an automobile. So you've always heard like, oh, it loses, blah, 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 the second you drive it off the lot. That's true, right? You buy a new car, it depreciates pretty quickly. And then it kind of slows down after that. The value of a car depreciates 15% each year. If a new car was purchased in 2024 for $32,000, find its value after 3 years, 5 years, and then when will its value fall below $10,000? So getting the initial equation, the starting value of this car, we're saying is $32,000. Times, remember this number starts at 100%. It's depreciating, it's losing value. It's losing 15%. So we're going to do 100% minus 15%, which leaves us with 85%. It retains 85% of its value each year. We're going to go with the decimal form, which is 0.85 to the x power. There's our initial equation. Let's see the value after 3 years. 32,000 times 0.85 to the third power. And we'll just round these ones to the nearest whole number. 0.85 to the third is 0.61 other stuff. Times 32,000. I've got 19,652. Cool. There it is. After 3 years, it went from $32,000 car to a $19,600 car. That's crazy. All right, 5 years. 32,000 times 0.85 to the fifth. 0.85 to the fifth times 32,000. 14,198.57. We'll round it to 99. So $14,199. Wow. Now figuring out when will it fall below 10,000, we're going to kind of have to guess and check. I see at 5,000 or at 5 years it's at 14,000. Let's pick another number. Let's try like 8 years. 32,000 times 0.85 to the eighth times 32,000. Oops, I did 320,000. So it's going to be in the 8,000s. So yeah, let me double check that. 0.85 to the eighth times 32,000. Yeah, so this comes out to 8720, which you're like, hey, 8 years, it's below 10,000, but it might fall below at 6 years or 7 years. Let's check 7 years. 32,000 times 0.85 to the seventh, 0.85 to the seventh times 32,000. That's in the 10,000s still. 10,258. So it's going to take 8 years for the value to fall below $10,000. Fun. Look at us, just real life applications here.